In this video, we'll be talking about geometric series and whether or not a geometric series or when a geometric series might converge or diverge. Now, from a previous video, you'll recall that a geometric sequence is something of the form of an equals r to the power of n, or again, some form of a sub n equals a r to the power of n. Now, a geometric series, however, is simply just taking that concept and turning it into, again, it's the sum of all the terms in that particular thing. So a, r, and now we're going to use k equals 1 to the power of n, so that this is to the power of n minus 1. Sorry, k equals 1 to the power of, k equals 1 to the n term of n. So this right here is actually going to be a geometric series. Now, what's important to note, this should be a k in here. What's important to note is that this series should continue all the way through n. Now, if we want to talk about an infinite series, that really should be an infinity symbol there. So the question is when does this type of series converge or diverge? Well, we only currently have one rule in determining whether or not a series will converge or diverge, and that's the use of partial sums. In which case, what I need to do is I need to come up with, well, s sub 1 equals s sub 2 equals s sub 3 equals, until I can get down to s sub n, such that I can take the limit of the nth partial sum and get the limit as n goes to infinity of s sub n equals to something. So, what we're going to do for this is we're going to use the concept of how geometric sequences work to help develop the geometric series in such a way that we can come to a conclusion about, well, what is this going to be, and therefore what is this going to be equal to, be it a convergence or a divergence. So let's start with what is s sub n. Well, in a geometric sequence, series, s sub n is nothing more than you plugging in 1 and then 2 and then 3 and then so on and so forth. So let's go ahead and start off with that. If I plug in 1 to this equation right here, I'm going to get a, and then r is to the power of 0, so no r. Plus, that's s sub 1, technically. S sub 2 will be, if I plug in 2 now, I'm going to have a r. Again, this is technically all these two pieces together is s sub 2. Then s sub 3 would be a r to the power of 2. Again, this would be s sub 3 if I were to look at this. This is the third term plugged in. And I continue this pattern until I end up with plus. If I plug in the nth value, I'm going to get a r to the n minus 1. So this is s sub n. And the goal then is to take the limit as s sub n goes to infinity, as n goes to infinity, and get that this thing is either approaching a number or it is not. So what we can do with this is we can attempt to try and manipulate it. Now, if you recall the example such that I proved that 0.9 repeating was equal to 1, we did this in such a way that it was 0.9999, so on and so forth. I split it up into 0.9 plus 0.09 plus 0.009 plus so on and so forth. And the algebraic way to deal with this was that I called this thing 0.9 repeating equals to x. And then I multiplied both sides, well, by 10. So how about in this example up here? Now keep in mind that this right here is nothing more than a geometric series. I can do the same thing with this that I did with this. Mathematically, it's the same concept. But this time I can't multiply by 10 on this example down here as I did up here. I can't multiply by 10 up here as I did down here. Multiplying by 10 down here was very specific because that was what I was changing each digit by. Up here, I don't know what I'm multiplying by every time. Well, I do. It's r. So what I'm going to do is I'm going to go ahead and take r. I'm going to multiply it by s sub n. This is going to provide me with ar plus ar squared plus ar cubed plus so on and so forth until I get to ar to the power of n. Now, in this example down here, I took the two values and I subtracted them from each other. So let's do the same thing up here. The way that I'm going to do this is I'm going to go ahead and I'm going to subtract s sub n minus r s sub n, giving me s sub n minus r s sub n. If I take, again, this stuff up here and subtract this stuff down here, a will be left over because a sub r is going to cancel out with a sub r squared is going to cancel out with a sub r squared, and so on and so forth until I get down to, well, this thing is going to cancel out with the one previous here, and a sub ar to the n is going to be left, so minus ar to the n. So now I have this little thing looking, it's kind of weird, but it's a thing. The next step that I took was, well, I needed to get out what x was, and x was supposed to be the entire thing. So in this case right here, I'm going to factor out s sub n, giving me 1 minus r. and then still equals to this thing here. You know what? I might as well just go ahead and factor a out on the top here as well, or over here on this side as well. So I'm going to go ahead and do that while I divide by 1 minus r. So s sub n, the nth partial sum for any term and any geometric series will be equal to a times 1 minus r to the n divided by 1 minus r. So now I've come up with a rule that is very consistent for any n value that I choose to plug in, such that I can find an r and an a. Now let's go through the concepts of what happens. So I need to know what is the limit as n goes to infinity of s sub n, which is the same thing as the limit as n goes to infinity of a 1 minus r to the n divided by 1 minus r. So the statement ends up coming out with the concept of, as n goes to infinity, for what values of, well, a doesn't matter, a is a constant, so it only depends on what's happening here. The a can be removed from the limit, and the limit as n goes to infinity of, well, what's going to force this entire thing to either be a number or increase or decrease uncontrollably, or just bounce back and forth. So that's what we're going to focus on. We're going to focus on this thing right here. Now, what's important to be able to do is to use concepts of numbers that won't work first. So the first number that's obviously not going to work is, what if r is equal to 1? Well, if r is equal to 1, then the denominator is 0, and this isn't possible. So the limit as n goes to infinity of a times 1 minus 1 to the power of n divided by 0, this doesn't exist. This limit is not even possible to consider, because I can't take the limit. Again, it's not me trying to plug in infinity and forcing the denominator to 0. No, I'm plugging in 1 for r, and mathematically this thing is undefined. So the limit doesn't exist, which means that this thing can't actually be a value. So if we were looking at r being equal to 1, we would say the geometric series diverges. Okay. More importantly, it diverges because it can't approach anything. Okay, so if I've picked 1 as an obvious value of issue, well, let's go ahead and try, well, what if I try everything greater than 1? Well, if I try everything greater than 1, then I'm going to have the limit as n goes to infinity of a times 1 minus r. I'm going to leave it as r to the power of n divided by 1 minus r. The important detail to note here is that if I'm larger than 1, this thing right here is going to get larger and larger and larger. Much, much faster than this thing here. Now, what we could do in conceptual understanding is we could attempt to multiply top and bottom by 1 over r and manipulate some stuff. And you'll find out that as r is larger than this number, though, that this top stuff is going to, again, continue to increase. So we would say that this limit, again, really does not exist, or more importantly, really is just uncontrollably large. The same is going to be able to be said for if we're less than a -1. Okay, if we're less than a -1, that means that this value right here, r, is going to be uncontrollably large, and it's going to approach infinity in some capacity that this thing can't even control or approach to. So that means that if r is greater than 1 or r is less than -1, we also have diverges. So the last detail we need to worry about is, well, what if r is between -1 and 1? Well, if r is between -1 and 1, I have the limit as n goes to infinity of a times 1 minus, again, r to the power of n divided by 1 minus r. The concept is that if I have a fraction in here, well, this is going to be a number. 1 minus a fraction is going to be a number, whether it's negative or positive. But this piece right here, as n gets larger, doesn't a fraction end up approaching 0? And if that's the case, then wouldn't this limit end up approaching, well, 1 minus 0, so a over 1 minus r, right? Because it's going to be 1 times a on top divided by 1 minus r. So if r is bounded between -1 and 1, then I'm going to say that this geometric series converges, and specifically it converges to a over 1 minus r. Now, be very careful with your understanding of what a is. We'll do some examples in another video, but a is the first term in this series. If I plug in 1, notice if I plug in 1 in this series, my a is this number. What if my starting location was at 5? If my starting location was at 5, then a here would not be the same as the a value here. So it's important to note that if I plug in 5 for this, if 5 is my starting number, then a r to the power of 4, that is the first term, and that first term is what's going to be up here. So that's what you're going to get for your A value. It's not, again, this A value. It happens to be this A value if the geometric series is in this form. But if the geometric series is not in this form and you're starting at a different value, then that A value here is not going to match up to this A value up here.